All right, so welcome to Design and Analysis of Experiments, STAT 568. This is the quarantine version of Design of Experiments from chilly, cold Edmonton right to your house. Right, so in the very first lecture that we'll be doing this year, what we'll be looking at is analysis of variance, specifically one-way ANOVA, and this is really the key point that we'll be starting from. We'll also be going through some various terminology as well because, well, we got to make sure we understand the lingo of design and analysis of experiments before we go forward. Man, you know, walking in the snow takes more effort than you think. All right, so welcome to our very first online lecture for Design and Analysis of Experiments, STAT 568, coming to you from the University of Alberta, or more or less from my basement down here. So in the first lecture, what we'll do is introduce the idea of ANOVA, the analysis of variance, which will be the main focus for most of this course. It's more or less the whole thing we do. But first, we also have a lot of terminology to set the stage, so it's a little bit dry, but it's good to make sure we understand all of the lingo before we go forward with this material. So let's get to the notes. So in this course, what we're trying to do is determine the difference in some value among different groups, which is an extremely vague way to put it at this point. But we have some examples. So for example, we might want to know, are the heights of Canadians the same or different between the various provinces? So we have 10 provinces in Canada, and we might want to know, well, are there differences in the heights of people? To do that, or to test that, what we could do is collect a sample of some amount of people from each province, measure their heights, and then ask the question, are the heights the same or different? We can compute a sample average of the height for each province, and then use the analysis of variance, ANOVA, to determine whether or not there's a significant difference there. Now, that would be what we would call a single factor. The idea here is that we have a single factor, which is province, and we want to know if that affects the height. Now, another example might be growing flowers. A lot of design of experiment is based on agricultural data. So, for example, we might have 3 different groups of flowers, different plots of land that we're trying to grow these flowers on, and we want to know, how do we get our flowers to grow the highest? So perhaps we want to give them different amounts of water, different amounts of nutrients, and other additives to the soil. These would all be different factors, and what we want to do is choose the factor levels, that is the amount of water, the amount of nutrients, etc., very specifically in order to determine how these factors affect the response. In this case, the response would be the height of the flowers. So let's get into some terminology first. So when we talk about running an experimental design, we have to know what the size of the test is. Sometimes this is referred to as the level. And the idea is this is the probability of a false positive. This is the alpha, often denoted as alpha, some number greater than 0, and what we're saying is what's the probability that we sort of choose the alternative hypothesis, H1 for our alternative hypothesis, given that actually the null hypothesis is true. And this probability would be alpha, which could be, say, 5%, 1%, whatever you like. It's the probability that we get a false rejection of our null. So in the case of the Canadian provinces, let's just say, you know, if we were to test heights across Canadian provinces, then, well, what do we have? Then the null hypothesis would typically be that the heights are all the same. I should be specific there. What I actually mean is not the heights are all the same, but the mean height is the same. What we're actually doing is we're testing for equality of means. So what we're assuming in the null setting would be that the average height, the mean height of citizens of each Canadian province is the same in each one. Versus the alternative hypothesis, let's adjust this, the alternative hypothesis, which is at least one province has, let's just say, taller or shorter residents on average. Remember, we're always looking at means in this case. So, of course, if you're looking at something like heights of two different populations, you may have some people who are just taller than average, some who are shorter than average, but what we're looking for is the mean, the middle of that bell curve distribution. And that's what we're really focused with here in design of experiments. So again, the size, which I will highlight here in blue, the size of the test, sometimes again called the level, is really just saying what's the probability that we would falsely claim that there are differences in the heights of Canadians in different provinces where there wouldn't be any. Now, I don't actually know if there is a significant difference in the heights of Canadians. I would assume not, just because of the general diversity and mixing of the provinces, but you never know. Maybe there are some significant differences that could be detected. And if we want to detect a significant difference, then we need power. So the power, statistical power, a test, this is the probability. Let me highlight that in blue to make it look better. There we go. So the power of a test is the probability of getting a true positive. The probability of, actually, what I guess I should say is it's the probability of rejecting the null, to be precise. The null hypothesis being our H0. So typically, power often is denoted by beta, the Greek letter, and it would be something like the probability that we reject H0. And again, this is all very qualitative. I'm not being precise in the definition. I'm just trying to give you an idea of what these terms mean for when we use them in more precise context in the lectures to follow. Right, so we have the idea of power. I also am going to say response a lot. So what is a response? A response variable. And this is, well, basically the thing we want to measure that we want to measure and test. So, i.e., this would be the output of our model. For example, it could be like the height in my hypothetical example of flowers or Canadian citizens. Now, if we have the output, we probably want to know what the input is. So the input to our model are going to be called factors. Maybe I should say factor variable. And these are going to be the inputs to our model. And in this course, in design of experiments, typically these will be discrete and categorical. I guess discrete, well, we'll just say and categorical. That is, we have something like the Canadian provinces. So in our model, we're not putting in, it's not like linear regression, where in linear regression, say we might want to put in somebody's age and get out their height. So as people get older, say through their adolescent years, they'll be taller, and we can use a regression to model that. In this case, we're actually going to be putting in a categorical variable like Canadian province and determine whether that categorical variable affects the height. So in this case, we would have 10 levels. I don't think I said what levels are yet. I should talk about that in the next one. We have 10 levels for our Canadian province factor. So I should actually write that down. Factor level. So this is the values that a factor variable can take. Right. So in this case, the example would be that the provinces of Canada, for provinces of Canada, etc. So Alberta, BC, Ontario, and the rest, etc. So the idea here is that these would be the input values to our model. The output, the response, would be the height of the citizens. I've used this example in classes for the last 3 years. I kind of want to test it now. If I could go out and find an actual data set, maybe Stats Canada has something we can use to actually see if there is a difference in heights, though I suspect they don't take the time to actually measure such things. All right, well, now that we have a factor level, we also have to talk about a treatment. So a treatment is going to be a combination of multiple factor levels. So what that means is that often after we get past, say, the first couple lectures, we're going to be considering experiments where you have multiple factors at once. So as in my example with the flowers, what we would have is we could have, say, the amount of water in, say, low, medium, high. We could have the amount of nutrients, low, medium, high. We could have sunlight, yes or no, right? These are all different factors we could include, and a given treatment would be a combination of these factors, a specific combination applied to one sample in our experiment. So it could be, for example, let's just say high water, let's say low nutrient, no sunlight, for example. And that could be one treatment that we would apply to one flower pot, and then get a response out of that flower pot. And then we would have a different treatment for a different flower pot, and so on. All right, we also talk about blocking. So blocking is about grouping subjects of a specific type in order to reduce the variation. So what we would have here is, let's say, blocking is to group subjects by a blocking. I guess I'm using the definition or the word in the definition, which is never good, but we're going to group subjects by a blocking variable to reduce variability. And the idea is that a blocking variable here is going to be something, I guess we aren't testing. But something that could still cause variability. So for example, e.g. for heights, we may block by male versus female. So in this case, that would correspond to a binary blocking variable. Binary because in this example, it would take on two values. And on average, right, not absolutely, but on average, men are slightly taller than women. So as a result, if we wanted to test for differences in average heights, we may want to block by male versus female in order to then determine the differences within each of these groups, or in that case, just to remove the variability that is present there. So that would be an example of blocking. And then lastly, there are different types of effects that we're interested in. So one of the main things we're going to look at is fixed effects. So fixed effects, and then the opposite is random, or the contrasting idea is random effects. These can be a little bit confusing, but we'll look at them a little bit more as we go forward. So a fixed effect is when factor levels are chosen by the experimenter. So most of the things that we'll be considering in this course are going to be fixed effects. Things like, again, the amount of a medicine to apply, the amount of, or in my example, the amount of water, or the amount of nutrients to give to your plants. Now the random effect is, well, basically the contrasting definition, which is a factor that's not controlled. A factor, we'll say, not controlled by the experimenter, like a subject, a person, an animal, a plot of flowers, for example, chosen randomly from a larger population. Right, so to give an example of this, we're going to look at this rabbit data set, which is in one of the standard packages in R. So let's do an example to kind of explain some of this terminology. So the example is going to take us to the rabbit data set from the mass, M-A-S-S library, package in R. And what they're doing in this is they're basically taking 5 rabbits and they're giving them different dosage of blood pressure medication. And then they're recording the response being the blood pressure in this case. So in this case, we have 5 rabbits. We have, let's see, we have medicine versus placebo. So are they getting the actual medicine, or are they just getting a shot of I guess, salt water or whatever it is that they're giving them? I don't actually remember the specific details, but we can look it up in the documentation later. And then there's a dosage. So in this case, what we would have is that the rabbits themselves, right, because each of the 5 rabbits is getting all of the different treatments. So the rabbits can be thought of as sort of a block by rabbit. But alternatively, you can also think of it as a random effect. I'll say and or random effect. One of the big differences between a fixed effect and a random effect is that a fixed effect, we're often interested in the value associated with each factor level. So if I have a high dosage of medication or a low dosage, I might want to know how that affects the response. For a random effect, I typically don't care. So it's like the rabbits here. Maybe one rabbit reacts really well to the medicine and one rabbit doesn't react at all to the medicine. In some sense, I don't care about that because they're just 2, or in this case 5, random rabbits selected from a population of effectively an infinite number of rabbits in the world that we could select from. So as a result, I don't care if one rabbit did really well or one did very poorly with respect to their response to the medication. What I do care about is the variability, because if the medicine has wide variability depending on the specific rabbits I pick, I need to control for that, or else it's going to just mess up my experiment. So in that case, we can think of the rabbit as a random effect. In this specific setting, right, we can treat it as a blocking factor because we're treating we have a nice setting in this experiment where we're actually testing every single treatment, every combination of dosage and medication on every single rabbit. And we'll get to this in later lectures when we talk about complete randomized block design. But for now, we'll just leave it at that. And yeah, just to finish my writing here, the medicine and placebo would be a fixed effect, we'll say categorical factor, and the dosage here would be my random effect. Oh, no, not random effect, sorry. Fixed effect. Ordinal factor. Ordinal in the sense that there is an ordering. Categorical meaning no order. So there's no natural ordering from medicine and placebo. It's just 2 different levels of my factor. Whereas for dosage, we have, in this case, I think there were 6. Yeah, there are 6 different levels from the lowest to the highest, and it sort of doubles every time. So in that case, right, there's a natural ordering, and we can use that in a later lecture to discuss how to treat an ordinal variable and to look for changes as you go from the smaller to the larger values, right? Because there's a little bit more information there than, say, with the Canadian provinces, where you would just have 10 provinces without any natural ordering, I guess, unless you wanted to go like east to west, but that's not exactly what we're thinking about. All right, so that's the first bit that we're here to talk about, which is kind of the introductory lecture on a bunch of terminology. It's pretty boring, but in the next round, which is going to start immediately, as soon as I update my camera here, what we'll be doing is actually talking about classic analysis of variant and ANOVA in the simplest setting. So I think what we'll do is I'll reset my camera and we'll jump right into that. All right, so now that we've gone through a bit of the terminology, let's go dig a little deeper and try to figure out exactly what's going on with analysis of variant in a more formal setting, right? So what's the setup here? So let's consider sort of a single factor like again, my Canadian provinces or otherwise, a single factor with K levels. 10 in the example of the Canadian provinces, my hypothetical example here. And for each level we sample n, little n, I guess, data points, subjects, maybe we'll say call it subjects, sample n subjects, for what becomes a total sample size of big N, which is going to be little n times K. Right now, you don't always have equal sample sizes for every of the K factor levels. It would be nice if you do. It's typically generally a nice setting, but you don't always have that. So you have to figure out what to do if that's not the case. But just for the ease of exposition, we're going to assume that they all have the same number of measurements or number of subjects in each category. And we'll denote, let's make sure I get this right. Yeah, I for 1 to K and J from 1 to N. Okay, so we denote Y, I, J to be the response measured for subject, or for, I should say, category I, that's the factor level, right? And subject J. Now, in this case, I would assume that subject J changes between each factor level. So that means I actually have, if I was doing this study with people, I would have a big N, a little n times K, total number of people. So if I have 10 Canadian provinces and I sampled 100 people per province, my entire study would have 1,000 people in it, unique individuals. Right, and then we also have to talk about randomization, because this is a very important point for the course. Randomization. So if we're doing design of experiments, we randomize everything. Possible. We randomize everything that's possible to randomize. So, e.g., we would randomly assign subjects to treatment groups. This doesn't really make sense in the case of my Canadian provinces example, because we would sample people who actually came from, we would sample people randomly from a Canadian province, but you can't just assign people to different provinces. But if we were actually doing something like a medical study, and we have our 1,000 participants in the medical study, and say we have 10 different types of medication or different treatment groups, we would randomly assign each of our subjects to a different treatment group. And that's beyond anything like when we consider blocking and other topics more advanced. But for now, we'll just say that if we have our subjects, we want to randomly assign them. And there's actually one other subtlety about randomization, which we'll talk about as we go further. But furthermore, we should test each treatment in a random order. So this will make more sense when I give you some applied examples that I'm working on to show what I mean by that. But in general, the idea is that if I have, say, a collection of different treatments to test, and I have to test them sequentially, like maybe I can just give everybody in medication and they all take it at once. But in the case that I have to run, say, a laboratory test, and I have to do one treatment after the next, or I can only do a certain number of tests at once, then what we should do is try to randomize the order completely so that the ordering doesn't have any effect on the response. What that means is, let's say I was doing some type of experiment on cell cultures, and I did all the placebos first, and then I did all the medicine treatment second. Well, then if something changed in the laboratory condition, like maybe it was later in the day, maybe it was hotter or colder or more humid, that could affect the outcome or the response. And it just so happens that because I had all the placebos first and all the medicine second, it may look like there's a significant effect there between the placebo and the medicine when there actually isn't. So that's why we would want to randomize. And if we had, say, two groups, placebo and medicated groups, that we would want to randomize the order and maybe do some of the placebo, some of the medicated, and go back and forth, vice versa. So again, when I have some applied examples that will illustrate this better than me just talking it out loud, but it is good to mention right here in the introductory lectures. Right, so let's write down a model equation, because we're going to be writing down a lot of these throughout the course. So now we have the, not ANOVA, but we'll say one-way to be specific, the one-way ANOVA model. So the one-way ANOVA model is simply going to tell us that our response, Yij, is going to be some population mean, mu, plus some treatment effect, tau I, plus some random noise. So let's write that all down. We have the ijth response. We have mu, which is the overall population mean. We have tau I, which is the ith, let's say, category effect. And we have epsilon ij, which is the random noise for the ijth observation. Right, so whenever we take an observation here, there's going to be some random noise that's going to correspond to, in some sense, everything that we're not considering in our experiment. If we're talking about the heights of flowers, well, maybe we had some faulty seeds, so they're a little bit shorter than otherwise. Or maybe there are other types of genetic differences in temperature, heat, things that we weren't actually considering when we did our experiment. That all gets shoved into the random noise. And hopefully we've controlled enough of the factors that that random noise term is fairly small. But we'll get into that going forward. But this is roughly the setup that we have. Now, for this course, we assume a couple things. We assume that the epsilon ij are IID, they're independent and identically distributed. Independent meaning that any two observations should not be dependent on each other. So if I have people in my study, there shouldn't be any correlations or dependence between the responses. So for example, if I'm running a medical study, I probably don't want to have siblings in my medical study because there's going to be some genetic dependencies there between them. And so ideally what we'll do is we'll assume that all of my Yijs, my observations, are all independent of each other. And furthermore, and we assume that they have a normal 0 sigma squared distribution. So, right, that means that our errors have mean 0 and they follow that nice bell curve that we love in statistics. This makes all of the mathematics nicer to work with. So it's a simplifying assumption. In practice, it does hold very frequently. And it's something that we can also test for to make sure that it holds when we're looking at our data. So we could run a test to say, do the errors actually look normal, in order to, in some sense, get some validation that what we're doing makes sense. If the errors are not normal, if they're skewed, if they have heavy tails, if there are other problems, then we have to worry a little bit more if our test statistics are actually valid. In that case, there are other approaches that are beyond the scope of what we'll talk about in this course, being non-parametric methods, rank-based method. There's a lot of different pretty cool stuff out there that you can do. Some stuff I've been working on myself, actually, but we'll leave that for another lecture. Right, so then the idea here is that for the, we'll say, one-way ANOVA model, what do we do? Well, we estimate the terms. So what we have is we have Yij. So the point is this thing is observed. So that means that we actually know what that is. We've seen Yij because we went out and we measured it in our experiment. But we don't know what any of the other things are in that equation. We don't know mu, we don't know tau, we don't know epsilon. So what we do is we try to estimate them. We want a mu hat. That's going to be our estimate of the global mean. We're going to get a tau I hat. That's our estimate of the ith category effect. That's actually the key thing that we're really interested in here, is we're interested in what's happening in each of the I categories. And what's left over is going to be denoted Rij, and this is the residuals. So if you've taken any course in linear regression, then you should be familiar with the term residual. The residual is really just looking at the difference between what the model says I should see and what my observation is. So I'll write this all down. Right, so we actually get these estimates, so we can write these down mathematically. Mu hat is really just what you think it should be, which is we take the average of everything we saw, and that's going to be our estimate of the global average. Now we can denote that as mu hat. It'll be convenient to write that as y bar dot dot. So this double dot notation means average over both indices. And this notation is going to be really useful because we're going to be averaging over the i's, we'll average over the j's. There's going to be later where we'll have k's and l's and even more indices. It's going to be kind of a mess at some points, but the idea is that we want to have a notation we can work with. So in this case, all we're saying is average over all the i's and all the j's. So we would take our big N here, and we would sum, in this case, I from 1 to k, and some j from 1 to n of the yij's. Again, we're assuming that each of the k categories has exactly n observations. That may not be the case in practice, but it does make the math a little bit nicer to write down, so we're going to do that for now. So we have that. We also have our estimate of the ith treatment effect. So in this case, what we're going to do is we're going to average all of the observations in category I, and we're going to subtract the global mean. So what we're really saying is, okay, if we take the entire population or the entire sample of our experiment, I should say, then we have one average. And then for each of the I categories, we can compute the average for just that subset of the experiment. And then say, well, is it a little bit above the global mean? Is it a little bit below the global mean? Where does it actually fall in here? Mathematically, well, it's nothing too profound. It's just going to be 1 over little n. 1 over little n here, the sum j from 1 to little n of yij, and then we're going to subtract the global mean, which is that same thing that I wrote over there on the left, which is I from 1 to k, j from 1 to n of yij. All right, so we have, let me just highlight these. We've got our mu hat, we've got our tau I hat, and then lastly, we have our residuals. So the residual are ij, right? Every single observation, yij, has its own residual, and that's going to be the difference between what we observed and what the category says it should be, the category average. So in this case, the residual is just going to be the difference in the observed and the category mean. So it's like saying, okay, we think that people in, I don't know, Alberta, say, are on average 5.5 feet tall. And then for every single observation, though, some will be a little bit taller than that, some will be a little bit shorter than that, and the residual is going to be the difference. It's going to tell us, in some sense, the how spread out our observations are around the category mean. Are they highly spread out? Do we have lots of really short and tall people in our province, or are they all about the same height? Is it very tight? That's what the residuals are going to tell us. Now, what this means is that we can take our model, which I think has, oh, no, it hasn't run off the top. We can take this equation here in green, underlined in green, and we can rewrite that in terms of y bars with various dots floating around. What I mean by that is that we can rewrite yij in a specific way, which is to say that, well, actually what we can do is we can subtract the global mean from it, or the estimate of the global mean, to be precise. So we subtract that, and then we can write two terms over here, which is going to be y bar I dot minus y bar double dot. And we can add to that the residual term yij minus y bar I dot. Okay, so mathematically that's kind of a stupid looking equation because, well, the yi dot or the y bar I dots just cancel out, and it's like, okay, well, who cares? The reason why this is useful is that we're going to square it, we're going to sum it, and now we're going to get our sum of squares decomposition, which is really the main thing we're trying to do in this course. So what I mean by that is that we'll say then square and sum to get dot dot dot. So what do we get? We get our nice sum of squares. There it is. Our nice sum of squares decomposition. There's tons of indices in this, so hopefully I'm not making any mistakes. If you think I messed up an index, just let me know. We're on video now, so there's any little errors I might have will be recorded for all of history. But what we do here, right, is we have our, we're going to sum over all I and all j, that is all categories and all observations per category. And what we have is something that looks like this on the left-hand side. So I'm just taking that term yij minus y bar dot dot, and I'm squaring it and I'm summing it, and I do the same thing on the right-hand side. When I do that on the right-hand side, well, a couple things happen. For this first term, if you notice, there is no index j, which means when I sum over that, I just multiply by n. So what that means is that I'll have something like I from 1 to k, and then n times y bar I dot minus y bar dot dot squared. And then we'll have a double sum again, I from 1 to k, and j from 1 to n. And we're going to sum over the squared residuals, which is going to be this term. And this is only the beginning of all the crazy sum of squares decompositions we're going to have to deal with in this course. But it is important to write this all out. So there's a couple of things to note here. The first is that, well, first I'm going to say down here, note that the cross term, which is the sum over y bar I dot minus y bar dot dot times yij minus y bar I dot is going to be 0 when I sum over all of them. So you can check that yourself. If you have any questions, though, please let me know, or we can talk during office hours and discussion time about that. But it's one of the nice things here is that there is a cross term, as when you square, right? If you do a square like a binomial, there's going to be a 2ab type cross term in there. In this case, when we sum over all the observations, it just vanishes, which is great, because then if we go back up to our sum of squares here, we have terminology for each of these pieces. So the left-hand side is what we will call the we'll call it SS tot for the total sum of squares. Now the first term on the right-hand side is going to be SS treat, TR, and this is going to be the treatment sum of squares. And lastly, we have the residual sum of squares, which I like to write as the error sum of squares, SSERR for error. And we'll call this the error or the residual sum of squares. Great. So what we're actually doing here is we're taking the total variation in our data, right? So the total sum of squares is kind of saying, what's the total variation, the squared sum of all the differences between each observation and the global mean? So that's in some sense the total variation that we have in our data, the spread of the data around the global mean. And we're breaking it up into two separate pieces. We're breaking it up into the variation that's coming from the treatment. That's the treatment sum of squares. And we have a second piece. The second piece is the unknown variation, or the variation coming from everything else that's not part of our experiment. That's the error or the residual sum of squares. So what we have here is we basically have that the SS tot, right, is going to be all variation in our data. Let's just say in our response, to be precise. In our response variable, the SS treatment is going to be variation due to the treatment And lastly, we have SS air, which is going to be variation due to other things, to be somewhat imprecise in my language. But the point is that this is kind of like the observed, and this is unobserved. But both are going to play a really important part when it comes to hypothesis testing. And that's what we're going to talk about next. So again, we're throwing a whole bunch of notation out here, but effectively all we're doing is we're just measuring a bunch of observations, yij, and then we're taking that sum of squares and we're decomposing it into two pieces. And those two pieces are going to be critical for hypothesis testing. So let's do hypothesis testing for one-way ANOVA. Take a sip and make sure, yeah, my thing's still recording. I'll be really sad if I end up not recording all of this. All right. So what are we doing? Well, in this case, we have two hypotheses to consider, and we talked about this in the first lecture in kind of a qualitative hand-wavy sense. The null hypothesis is typically the one where there's nothing interesting to see here. In this case, our null hypothesis would be that all of the treatments have the exact same effect. So all treatments, well, I could say treatments or factor levels, but we'll just say, we'll say treatments here. All treatments have the same effect on the response. So again, this would be the case where all of the different medicines I'm trying, all of the different fertilizers I'm trying, all of the different Canadian provinces have no effect on the response variable that we're trying to measure. But for the alternative hypothesis is that there exists, to be precise in the language, there exists, we'll say an I, let me get rid of that, I1, and an I2, such that tau I1 is not equal to tau I2. So this is basically at least one pair of treatments differ. So in some sense, the null is there's nothing interesting to see here. The alternative says there's at least some difference among all of our different treatment groups, among all of our different categories, among all of our different factor levels. And then, of course, there's follow-up testing like, well, okay, if there is a difference, then where is the difference, right? We might want to know that. But for now, we just want to know, is there actually a detectable difference here? This would be something that we would consider like a global test. We're just testing over all the categories. Is there something worth looking at here, or is it not interesting and just throw away? No one would never throw away the data, but you know what I mean. Okay, so we can do this. So mathematically, we'll say, assuming that the epsilon ij are IID normal 0 sigma squared, which is, again, the big assumption that allows us to do parametric statistics in this setting, then what we find is that the error sum of squares happens to follow a chi-squared distribution with degrees of freedom n minus k. So mathematically, again, assuming that our errors have a normal distribution with equal variances, sigma squared, for all of them, then what we have is that the error sum of squares has a chi-squared distribution with n minus k degrees of freedom. Now, we'll discuss this more precisely in the lecture on Cochrane's theorem, which will come later in the course. But for now, let's just go with it, and we'll make it more precise later. If you want to know, the chi-squared distribution is going to look something like this. It's going to have it's positive valued or non-negative. I guess, yeah, it takes values. It's non-negative valued, and it is sort of skewed in the sense that it extends from 0 to plus infinity. So this is our chi-squared distribution over here. And degrees of freedom is going to be a really critical part of this course, and we'll be discussing that a lot, to the point that it's probably going to annoy everyone. But it is really important to be able to count degrees of freedom, and that's going to be one of the main things we're going to be doing in this course. But at least right now, it's not so bad. Okay, I'm getting a little bit sidetracked on my tangents. The point is that the error sum of squares under this assumption will have a chi-squared distribution. And under the null hypothesis, we have that the treatment sum of squares also has a chi-squared distribution. In this case, the degrees of freedom is going to be k minus 1, the number of factor levels minus 1. This is specifically under the null hypothesis. Now, under the alternative hypothesis, what we have is that the treatment would have what we call a non-central chi-squared distribution. And the whole idea is that we can use this now to do the testing that we want to do. So basically, this difference here, let's get a different color for my arrows. This difference here, allows for testing that we want to do. So that's what we're going to do. Is we want to know is basically, right, we're going to look at our treatment sum of squares, and we're going to ask the question, well, does it look like it has a chi-squared distribution, or does it look like it has a non-central chi-squared? Now, you don't need to know the definition of these distributions precisely, especially the non-central chi-squared is just kind of like a shifted chi-squared. Okay, there's more subtleties to the definition that I'm not going to get into, but the mean is shifted a bit. The distribution itself isn't shifted, but the mean is kind of shifted. But anyway, the idea is that we want to use these tools for hypothesis testing. So our test statistic, so the test statistic we use for the above hypothesis test is the fabled F statistic. F for, I believe, Fisher, our founding father of statistics, or one of the key founding fathers of statistics. So F, though, now that I think about it, I think there's actually the name Snedeker attached to the F test. I have to double check that. Who is another famous, if less known than Fisher, statistician. Regardless, the F statistic. So the F statistic is going to be the ratio of our treatment sum of squares to our error sum of squares, but we have to normalize by the number of degrees of freedom. In this case, k minus 1 and big N minus k in the denominator. And the idea is that this is going to have an F distribution to sort of abuse the notation and just keep writing capital F everywhere, with k minus 1 degrees of freedom and capital N minus k degrees of freedom. And this is under H naught. So this is under the null hypothesis. So what this means is that we now have something that a test statistic. And what's a test statistic going to tell us? It's going to give us a value that we can use to determine whether whether we should not reject the null hypothesis, or if we should reject it in favor of our alternative hypothesis. Pedantically, in statistics, you would never say you accept the null hypothesis. You would say that you fail to reject it. So sometimes people can be very precise. Try to be precise about the language. So in R, or any stats package that you like, so we'll say on a computer, e.g. in R, we get an ANOVA table. And looking at ANOVA tables is basically like 70% of what we're going to be doing in this course. In this case, what we'll have is we'll have two rows. We'll have a row for our treatment, and we'll have a row for our residuals. And what we get is a couple things. We have our degrees of freedom. Again, this is going to be important because the degrees of freedom are going to tell us, in some sense, how many hypotheses we can test, and based on our data size and the number of factor levels for each factor variable we have. We're also going to have our sum of squares, which in this case is just going to be the treatment and the error sum of squares. We're going to have our mean squared, which is the normalized sum of squares. So in this case, what we're doing is we're just taking our sum of squares and we're dividing it by its degrees of freedom. In this case, k minus 1. And in the other case, we're dividing by n minus k. And then lastly, we're going to have our f value, which is just the f statistic that I wrote up on the side here above it. And we're going to have a p-value. And this is the final and key piece of the puzzle, which is the probability of observing basically it's a tail probability. So what is a p-value? So a p-value is really just going to be, in this case, it's going to say what's the probability of observing a test statistic that is an f value under the null hypothesis, more extreme, e.g. that's, or not, e.g. i.e. to get my, if it'll erase, it's not erasing for me. Huh. There we go. i.e., what was I saying? Larger, that is, than what we observed. So in a picture sense, what we have is we have something that's going to look like an F distribution. I forget what the F distribution looks like, to be honest, and then depending on the degrees of freedom, it changes a lot. remember the F distribution has 2 different degrees of freedom, which is still at the top of the page here. In this case, we have a first degree of freedom, which is corresponding to the numerator, the k-1, and we have a second degree of freedom, which is corresponding to the denominator, the n-k. And I'm certainly going to be examining you on those degrees of freedom, so make sure you learn those. But anyway, the idea is that the F distribution, let's just assume it looks something like this, depending on its degrees of freedom. Then what we do is we have an observation value F here. And what I want to know is what's the probability that I would see something out here. So in green, this is the p-value. Mathematically, what we're saying is what's the probability of observing. I need another variable, so maybe we'll just say F star greater than F under the, well, it doesn't have to be under the null hypothesis because I'm just assuming that where F star has an F distribution with those degrees of freedom, 2 degrees of freedom, as I just said, that we would see under the null hypothesis. So the point is that the conclusion is that if the p-value is small, where that's sort of up to the discretion of the experimenter, we'll say less than, say, 5%, but that seems a bit big in my opinion, maybe less than 1%, or less than 0.1%, or whatever you think is a good threshold to choose. Then reject H0 in favor of H1, our alternative hypothesis. Otherwise, we don't reject. A bit of a double negative, but again, it's sort of the pedantic way to say it. And that's more or less what we're doing here. So, all right, what else do we need to do? Well, let's talk a little bit more about degrees of freedom before we go forward. Yeah, because I think we have, yes. All right, so degrees of freedom. So the way we can think about this intuitively, for at least in our, well, in some sense in all cases, but specifically in our one-way ANOVA, is that it is the sample size minus the number of terms to estimate. So, for example, for the air sum of squares, we have capital N Yij's and estimate, and what we're doing is we're estimating k tau i's, right? So we have our giant sample of capital N data points, and we're estimating k different treatment effects for each of the k categories. For the treatment sum of squares, we have k categories, and we estimate one global mean we'll say mu hat or y bar dot dot. So that's intuitively what's going on. And then what we're doing is we're taking that sample size, capital N, and we're subtracting the number of things we estimated, little k. Or in the treatment case, we have the number of things we have, which is k different categories, but we have to center them. We around one global mean, so that's what we estimate, and we subtract 1. So intuitively, that's kind of what's going on. Again, we will make degrees of freedom more precise when we talk about Cochrane's theorem, which is the one really mathematical piece of this course. Otherwise, it's going to just be a lot of counting, and there is a lot of intuition behind it. You can think of degrees of freedom in some sense as the currency of design of experiments. Every degree of freedom is going to allow us to estimate something and test something. So it is very important to know what your degrees of freedom are for your experiment. It's also really important because when you plug in your data and your model into R, it's really easy to mess it up and to get something wrong. And one of the best ways to check to make sure you're doing everything right is to count degrees of freedom. Because if you plug in your equation wrong, you can very easily get some strange degrees of freedom that don't make sense. And it's a very quick way to check and say, I made a typo in my code, for example. Right, so now let's see what we're doing. Yeah, I think we can, let's push forward and discuss a little bit about linear models. So linear models. So the one-way ANOVA, and in some sense everything we're going to be talking about in this course, not just one-way ANOVA, is a linear model, i.e. it's basically just linear regression. So assuming that you've seen linear regression, we're not going to go into the great details about it, but it is good intuition, especially if you're comfortable with the idea of linear regression, or if you happen to take one of the great linear regression courses we teach at the University of Alberta in the fall term. Sadly, I'm not teaching that this year, but I'm sure it's perhaps even better than it was in the previous years when I was teaching it. Regardless, what we have here is we have our general linear model setting, which is y, our response, is going to be a linear combination of x. X is our design matrix, beta is our vector of parameters, and epsilon is our errors. Here, we would have that beta is going to be a big vector of our parameters that we want to estimate, which in the case of one-way ANOVA is the global mean and all of the tau 1 through k. Okay, so, oh yes, and I should also probably point out what x is. X is our design matrix, and it's going to look horrendous. It's just going to be a giant matrix with lots of ones and zeros. So what it will look like, just for the sake of writing it out, is going to look something like this, where you're going to have ones in this peculiar kind of diagonal pattern going all the way down, and then zeros everywhere else. I have a slightly nicer version of this in my typed notes online if you want to look at it. But effectively, the point is that x is a capital N by k plus 1 matrix of zeros and ones. Great. And what we have is that, I'll say from linear regression, we have the least squares estimator, which is effectively what we're trying to do. The least squares estimator for beta, which is beta hat, is going to be in matrix notation x transpose x inverse x transpose y. All right. So again, I'm kind of assuming that you've seen this before. I'm not going to go into all the details of what the least squares estimator is. It's the one that minimizes the sum of the squared error, but mathematically, we're not going to go into all the details. I just wanted to point out that you can think of one-way ANOVA as a linear regression problem. And when you do that, what you get out is just the least squares estimator. Well, you almost get it out. See, there's actually a problem here. There is a problem, which is that X transpose X is not invertible. And this is going to be a really key thing to understand when you plug in your data into R or whatever stats package you like to use. Because you're not going to get estimates for all of your parameters, you're going to lose one of them. And it's because of this idea of invertibility or identifiability. So the point is that, as stated, the parameters are not identifiable. So what does that mean? Well, that means that, right, if I have an equation like yij is going to be some global mean plus tau I plus epsilon ij, well, that's the same, right? That's equivalent to basically writing yij is going to be mu minus 1 plus tau I plus 1 plus epsilon ij. So the idea is that, well, I can't estimate all of these terms because, well, I could always just subtract one from the mean and add one to all of the treatment effects, and it would give me the exact same thing. It looks like my battery is about to die on my camera. Luckily, I've got another one, so I might have to switch over to that in a second. But let's see if we can finish up what I was trying to discuss here. Yeah, so the idea is that we have an identifiability issue. We are not able to estimate all of these terms uniquely. So effectively, what we need to do is we need to, so hence, we need, if I die on the camera, actually, I guess you can just listen to my disembodied voice as I finish this section. So hence, we need an additional constraint, I should say linear constraint. We need an additional linear constraint to make this work mathematically. One of the standard ones that you would do, for example, is to set the kth treatment to be basically the negative of the sum of k minus 1 tau I. Okay, so that might seem a little strange at first, but this is what R does by default. By default. So if you were to actually analyze data in R, you wouldn't get an estimate for whatever the final category is. You would only get a global, well, yeah, you would get, I guess there's actually, no, I'm wrong. It doesn't do this by default. Sorry. That's actually wrong. R doesn't do this by default. R removes the global, well, okay, it removes it, how do I want to say this? R sets tau 1 plus mu to be the global mean. So what R actually does, up and there goes my camera. Well, that's okay. I'm going to finish this train of thought and then we will pick up again with an example in the next part of this lecture. But effectively what R does, right, is it sets tau I or tau 1 plus mu to be the global mean. So in this case, it's determining the first category as kind of the default or the control. So that means that the first category becomes a default or control group, and then all of the other estimated terms are looking at the differences between that first category and the subsequent 2 through k categories. Alternatively, you can do what I was trying to do above with this tau k is equal to the minus sum of the tau i's, which is really just centering everything around a global mean. But now that I think about it, this will be much more precise if I fire up RStudio and we actually look at an example. So that is what we will do in the next lecture. I'll actually give you an example of how this works in practice, and then we'll continue on from there. So with that, I think we will end this version of the recording and see you in the next lecture.